In this video, we'll be going through some science questions, specifically physics questions. So let's go ahead and start. Now, the first question says, how many significant figures are in this particular number? 2.0800. What would you say? Well, when you're dealing with significant figures, there are some rules that you want to be familiar with. The first one which we can look at is that all non-zeros are significant. So in this case, 2 and 8 are actually significant. Keep in mind, whenever you see non-zeros, then just know that they are counted, they are significant. Now, the second point is all zeros that are between non-zeros are also significant. So zeros between non-zeros are significant. So in this case, when you see a number like this, 2.0800, then just know that this zero here is also significant because it is between the two non-zeros. Now, the third rule is zeros at the end of non-zeros are also significant. So in this case, you have two zeros at the end. Just know that those two zeros are also significant. So which choice are you going to go for? Notice that for A, you have 2. Now this 2 perhaps is just counting the two non-zeros, 2 and 8. And this is obviously wrong. Now, when you look at B, notice that it says 3. Now this 3 perhaps is just including 2 and then this 0 between two non-zeros and this non-zero, which is 8. But that is also wrong based on the rules. And C is saying 4, which is also wrong according to the rules. So the best answer for this particular question is actually answer choice D, because it is trying to show that you have 5 significant figures, 2, 0, 8, 0, 0, based on these rules. So make sure you understand these rules because they are going to help you deal with problems on significant figures. Almost all the problems on significant figures can actually be tackled when you understand these rules. So make sure you keep these points in your mind. Now the next question is, which of the following contains base physical quantities? Base physical quantities only. What would you say? Well, the first thing that we can look at is we have what we call base quantities and we have what we call the derived quantities. Now, when you're talking about base quantities, you're talking about things like mass, which is measured in kilograms. You're talking about time, which is measured in seconds. And you're talking about length or distance, which is measured in meters. Now, these are base quantities because they are not derived. Notice that when you look at the units, they have single units like kg, seconds, meters. When you're talking about derived quantities, you're talking about things like acceleration. Now, the units for acceleration are meters per second squared. Now, when you're calculating for acceleration, it is given by final velocity minus initial velocity over time. Now, this means that whenever you are trying to calculate acceleration, it is dependent on these things that we have here. Final velocity minus initial velocity over time. So you have to derive it from these figures to get it. So this is a derived quantity. That's why even the units are meters per second. Meters, which is for distance, seconds for time. So that is a derived quantity. The same is true for speed. when we're talking about speed, it is measured in meters per second. Now, speed is actually distance over time. So again, for you to find speed, it is dependent on the two things that we have here. So it is derived from distance and time. That's why it is meters per second, showing that it is a derived quantity. The same is true for velocity, which is also in meters per second. So these are derived quantities. In other words, they depend on certain things for them to be calculated. Whereas when you come to mass, you realize that you can actually find mass without depending on anything. You can find time without depending on anything. You can find distance without depending on anything. So make sure you understand that these are base quantities and these are derived quantities. So when you come to the question here, this is dealing with base physical quantities, which means that you're dealing with things like mass, time, and distance. Now, which of the following contains base physical quantities only? This question is dealing with the base physical quantities, but it is also trying to show the standard units for these base quantities. So the only two base quantities we have here are length and mass. Now, when you look at option A, you have length, which is the base quantity, and mass, which is the base quantity. Now, what are the correct units for these base quantities? Notice that for length, which is distance, it is given in kilometers. However, the actual units or the standard units should be meters. So we can eliminate this answer because length is actually used in kilometers. So we can also eliminate, by the same token of logic, answer choice C, because even here length is in kilometers. It should be in meters. Now we remain with options B and D. Notice option B that mass is actually in tons. However, mass should actually be in kilograms. So we can eliminate this answer choice as well because mass is in tons. That's not the standard units for mass. So we just remain with option D. Notice that length is in meters and mass is in kilograms. So this is the correct answer which we are going to go for. It shows the base quantities and also their standard units. So make sure you understand the difference between base quantities and also the derived quantities, and also understand their actual units. Know how to distinguish between them, and then whatever question you might have on base and derived quantities, you'll be able to deal with them. Now, the third question is, the following shows the steps that a learner carried out in order to determine the volume of a wooden cock. So you have step 1 here, you have steps 2 and step 3. Now the question is, which one is the volume of the wooden cock? Now, the first thing that you need to understand here is that you are trying to calculate the volume of an irregular object. In this case, you might have a rock which you cannot easily measure. So how do you measure the volume of an irregular object? What would you say? Well, the first thing that you need to do is you have to get a cylinder and fill it with water. So let's say we fill this cylinder with water up to 10. And the second thing is, when you try to put in this particular object which is irregular, then you're going to realize that the water level is going to increase. So you still have the object inside, so it's going to be like this, and you have a string there, and the volume is now going to go to this position. So let's call this 20. So how do you find the volume of this particular irregular object? Well, the volume should be given by the final volume here, which is volume 2, minus the initial volume here, which is volume 1. So in this case, you're going to get volume 2, which is 20, minus volume 1 here, which is 10. So the volume is going to be 10 cubic centimeters. So that's how you find the volume of an irregular object. So this is what is happening here. When you look at the question, notice that for the first step, you have water in this cylinder. Now, the water level is actually up to the 50th mark. So we can confidently say that the first volume is actually 50 cubic centimeters. Now, one glass bulb has been added in the second step. When we add one glass bulb, notice that the volume of water increases from 50 to 60. So we can say that the volume for one glass bulb is actually 10 cubic centimeters. Why? Because after adding it or putting it into the cylinder, the volume increases from 50 to 60. Now, when you look at the third step, notice that you have two identical glass bulbs. So because you have two identical glass bulbs, it means that you have two of these. Since one glass bulb is 10 cubic centimeters, then two of them, two glass bulbs, will give you 10 plus 10, which is 20 cubic centimeters. So just keep that in mind. Now, notice that at this stage, the volume of water increases from 60 to 100. From 60 to 100. And this is after you've added one more glass bulb and this wooden cork. This implies that the volume for one glass bulb plus this wooden cork is actually 100 minus 60, which is 40. Now, you have 40 cubic centimeters for this wooden cork and the glass bulb. But you know that one glass bulb is actually 10 centimeter cubed. So you can easily see that if you want to find the volume of the wooden cork, you can simply subtract 10 cubic centimeters from 40 cubic centimeters for one glass bulb, which is there, and you're going to remain with 30 cubic centimeters. So this is going to be the volume of this wooden cork, 30 cubic centimeters. So our answer in this case is going to be answer choice A. This is the correct answer. Now, you might also be asked to find the volume of a regular object. For a regular object, you don't need to use this method to find the volume, because you might have a regular object like this. Let's say you have a wooden block like this. And let's say this is 20 centimeters. And let's say this is 10 centimeters. And the height here is, let's say, 10 centimeters as well. To find the volume of this regular object, all you have to do is use the formula volume is equal to length times breadth times height. So this is the length, this is the breadth, and this is the height. So you're going to say volume is equal to, the length is 20 centimeters, the breadth is actually 10 centimeters, and the height is also 10 centimeters. So the volume is going to be 2000 cubic centimeters. So that is going to be your volume. So keep in mind, when you're trying to find the volume of regular objects, you simply use this particular formula to find the volume. However, when you're trying to find the volume of irregular objects, then you use this method where you have a measuring cylinder, you put some water, you calculate the initial volume, you add the object which you are measuring, and then find the final volume, subtract the two, and you have the volume of that particular object. Question 4. Which of the following diagrams show an accelerating car? So which car is accelerating in this particular scenario? Well, you have to understand that acceleration is the rate of change of velocity. So acceleration is equal to the rate of change of velocity with time. Now, velocity is more like speed, except that velocity is a vector quantity, whereas speed is a scalar quantity. Now, what you need to understand is when you look at the options here, notice that you have distance here and you have time on the x-axis. So this slope here is trying to show how much this velocity is changing. And when you know how much the velocity is changing, you can know that that is acceleration, because acceleration is simply how much or how the velocity of an object changes. Now, for a car to be accelerating, the velocity itself, because this is the rate of change of velocity, then the velocity itself should be changing. And in this case, the slope is representing the velocity of this particular car. So, which diagram shows the velocity which is changing? And it's not just about changing, it is about changing in a positive direction where the velocity is increasing, not decreasing, not constant. So let's test option A. When you look at option A, notice that velocity moves from point 0, but although the time is changing, because notice that in this direction you have time which is changing, in this direction you have distance which is changing. So this slope is showing that time is changing, but notice that the distance is actually decreasing because it is moving away from this y-axis. It shows that this distance is decreasing. And because the distance is decreasing, this shows that this is not increasing. The velocity is not actually increasing. That is not showing positive acceleration. Instead, it is showing negative acceleration. When you look at option B, this is showing that the distance is changing significantly. When the slope is steeper like this, it shows that this velocity is actually changing positively with time. And this is showing positive acceleration. This is constant. Notice that it is not changing. It remains constant like this. And this is also not showing a car that is accelerating because the distance is not changing at all in this particular case. Notice that it is just like that. It is not changing. So the best answer for this particular question is actually option B, because it shows that this velocity is changing positively with time. When the slope is steeper like this, closer to the y-axis, just know that that is positive acceleration. When it is not steep, where it is going far away from the y-axis, just know that that is negative acceleration. But since the question is talking about the car that is accelerating, then option B is the best answer for us. So make sure you understand how these travel graphs work, how you can show that the car is accelerating or decelerating and so on. Now for question 5, it says the diagram shows a light bar PR pivoted at P. So this is the pivot and it is balanced by a 4 newtons weight and force F. So the question is, what is the reading on the Newton balance? Now this is demonstrating the turning effect of forces. When you're talking about the moment of force, you're talking about the turning effect of force around a pivot when that force is applied on an object which is at a perpendicular distance from the pivot itself. So let's say you have this particular wood. This is the wooden block, and let's say this is a pivot. So let's say we put an object here and we'll put another object here. So this object is having the weight of 20 newtons, and this one is also having the weight of 20 newtons, and the distance from the pivot is actually the same. Let's say it is 2 meters and here it is 2 meters. So the reason why this pivot is balanced, it is not going this direction or this direction, is because notice that the forces are balanced together with the perpendicular distances. Now, the distance here is perpendicular to the application of the force. The weight is in this direction, the distance is in this direction. So the distance is perpendicular to the direction of weight. Now, you can calculate the moment of force. So the moment of force is going to be given by force times perpendicular distance. So in this case, the moment of force on this side is actually force, which is 20 times distance, which is 2. So the moment of force in this case is going to be 40 Newton meter. The same is true for the moment of force on this particular side. So it is going to be the same, where you are going to get the moment of force is equal to 40 Newton meter. So because the moment of forces are balanced, then the block here, or the wooden block, is actually balanced at the pivot. So you can think of it like you have something that you've put on the pivot and one person sits on this side and another person sits on the other side. You can actually balance that block on the pivot by adjusting the distance. Because in this case, if we try to move this object to this direction, you will see that this object is going to go down. The balance here is going to be disrupted. So that's basically what we mean when we're talking about the moment of forces. We are trying to compare the turning effect of forces regarding the force and the distance on one side and the force and distance on the other side. Now, what is demonstrated here is actually what we call the principle of moments. The principle of moments states that the sum of the clockwise moments must be equal to the sum of anti-clockwise moments. So when these two are equal, then the object is actually balanced at the pivot. So let's go ahead and look at the question that we have. Now, when you look at the question, notice that we are trying to find the reading on the Newton balance here. Since this is the pivot at P, then the turning effect is actually taking place around that point. Now, the object is actually placed at Q. Notice that this is the object at Q. Since we are interested in finding the reading on the balance here, you have to understand that it is the reading of this object in relation to its pivot. Now, whenever you're trying to find the force in this case, you apply what we call the principle of moments. So the sum of the clockwise moments must be equal to the sum of the anti-clockwise moments. So in this case, we are going to have the clockwise moment is going to be force times distance, which should be equal to the sum of the anti-clockwise moments, which is also force times distance. Now, what we are going to do here is that we want to know the force that is going to be read at this balance in relation to the pivot. But we also have the force here in relation to the pivot. So we're going to use the two here to find this particular reading here. So for the first one, notice that this force here, or weight, which is 4 newtons, in relation to its pivot, from this point to the pivot, you have the distance of 30 meters. So that's the first thing that you are going to get. So you are going to have 4 newtons times the distance there, which is 30 centimeters. And then For this force that you are finding the reading here, this is going to be this force times the perpendicular distance, which includes 20 and 30. So you're going to have the force that you are looking for times the distance here is 30 centimeters plus 20 centimeters. So that's what you're going to have. And when you multiply this, you're going to get 120. And you're going to have force times 20 plus 30 is going to give you 50. So this is going to be over 50 over 50. So force is going to be 120 over 50 is actually going to be 2.4 newtons. So this is going to be the reading on the Newton balance. So the answer choice for us is actually answer choice B. So that is showing the correct answer when you do the math there. So make sure you understand what the moment of force is and the principle of moments and how to apply the principle of moments. Just understand that this is showing that the sum of the clockwise moments must be equal to the sum of the anti-clockwise moments. When these two moments are actually balanced, then you know that you have a balanced object at the pivot. Question 6. A car is traveling on a level road. Suddenly, the driver of the car sees a cow crossing the road and decides to apply brakes. What are the energy changes as the car slows down? What would you say? Now, the first thing that you want to be familiar with is what we call the law of the conservation of energy. So this law states that energy can neither be created nor be destroyed, but it can be changed from one form to another. This is the law that we are going to apply here. The law of the conservation of energy is important. It shows that energy can neither be created nor destroyed, but it can be changed from one form to another. So what are the different types of forms of energy that we can talk about? Well, we have kinetic energy, kinetic energy is the energy possessed by an object in motion. The word kinetic points to motion. So when something is moving, then it is using kinetic energy, or it is in possession of what we call the kinetic energy. When an object is at rest, it possesses what we call the potential energy. So when an object is at rest, it possesses the potential energy. Typically, these are the two main forms of energy that are quite discussed when you're dealing with O-level physics. But you have thermal energy, you have sound energy, and so on. So these are the different forms of energy. In other words, energy cannot be destroyed, it cannot be created. It can simply be changed either from kinetic energy to potential energy, or from potential energy to thermal energy, or from thermal energy to sound energy. So keep that in mind. Now, in this scenario that we have here on this question, notice that a car is moving. So since this car is moving, so let's say this car is moving like this. What type of energy do you think it possesses as it is moving? Well, the fact that it is moving shows that this car possesses what we call the kinetic energy. Now, notice that the driver sees the cow crossing the road and then he applies the brakes. What are the energy changes as the car slows down? Now, you can eliminate answer choices A and B because it's like the initial form of energy possessed by the car is chemical, which is not true because it should be kinetic, and it is not heat, it should be kinetic. So we can eliminate the two choices there. Now, what about option C? Well, when you apply the brakes, what happens? What happens is that there is too much friction between the tires and the surface of the road. So because there is this friction, what is going to happen is that the more friction you have, the easier it becomes to actually produce some heat between the tires and the ground. If you try to rub something together with much force, you realize that it's going to start becoming warm. The reason for that is because that kinetic energy is now being converted to what we call the thermal energy or the heat energy. That's why you feel some heat when you are trying to rub the two things together. So the kinetic energy is being converted to the heat energy. And in this case of the car, you see that when the driver applies the brakes, not only is it going to have that much friction with the ground, but you also hear some sound. You can think about that. When the car stops suddenly, there is friction, which means that there is thermal energy there, but also there is sound because there is that friction. So you see that the conversion here is not from kinetic to chemical and sound. The conversion actually should be from kinetic to heat and sound. Heat in the sense that because of the friction, you're going to see some thermal energy there, or feel some thermal energy there, and also you're going to hear some sound. So this kinetic energy is actually converted to heat and also to sound. So make sure you understand these different forms of energy. Question 7 says, the graph below shows a cooling curve of a gaseous substance. Now, in which states of matter will the substance be between points F and G? Points F and G. What would you say? Now, this is a cooling curve. The cooling curve shows how the temperature of the substance changes as it is being cooled. So you are cooling the substance. In other words, you are decreasing the temperature. So the temperature is going down. This is what we call the cooling curve. So there are three states of matter. You have solids, liquids, and gases. So in solids, you know that particles are closely packed. In liquids, particles are loosely packed. In gases, they are widely packed. Now, this means that when you're talking about the change of state, you can change the state of matter from solid to liquid. This is called melting. Now, you can also change from liquid to gas. This is called boiling. Now, the opposite is also true. Like you can do the opposite of this where you convert the liquid to solid. That is called freezing. And from gas to liquid, that process is actually called condensation. And you can also change from gas directly to solid, or from solid directly to gas. That process is actually called sublimation. So keep in mind, because this is going to help you understand cooling curves and also heating curves. Now for cooling curves, what you're doing here is that you're trying to move from gas to solid. So this is our movement here. In this case, we are moving from gas all the way to solid, but it's from gas first to liquid, then from liquid to solid. And keep in mind the temperature is actually decreasing. Now you realize that then this means that because we are decreasing the temperature or the energy in this direction, then the starting point here is the gaseous state of matter. So E is pointing to gas. Now from E to F, the temperature actually decreases significantly, which means that we are trying to condense this gas. Now when it reaches F, notice that the temperature remains constant between F and G. Now the reason why that temperature remains constant is because that temperature is no longer being used to reduce the kinetic energy of particles, because the gaseous state of matter is in a state where particles are moving rapidly because they have too much kinetic energy. By reducing this kinetic energy, you start bringing these particles together. In other words, the intermolecular forces of attraction start to bring these particles together. As a result, the gas particles actually cooled and they become like liquid. So this happens when you remove the kinetic energy. But at the point where these particles are now changing a state from gas to liquid, the temperature remains constant because the temperature is no longer being used to convert or to reduce the kinetic energy of particles. Instead, it is now being used to change this state from gas to liquid. That's why the temperature remains constant at this particular point. It remains constant once again because it is no longer being used to reduce the kinetic energy. Instead, it is being used to change the state of matter from gas to liquid. So based on that, you can clearly see that at point F, condensation begins, which means that at point G, you have the liquid state of matter. This gaseous state is completely changed into the liquid state. And then the process continues again. You reduce temperature significantly between G and H. And at H, again, you see that the liquid is now converted. It is now going through the process of freezing. That's why the temperature again remains constant. And when we reach point I is actually solid. So this is what is happening. The opposite of this is actually what we call the heating curve. Now, in which states of matter will the substance be between point F and G? So what would you say? Point F and G, we have this point and this point. Now, at this point, notice that this is condensation. The gas is being changed to the liquid. That's why the temperature remains constant. If that is the case, then during this process, you have gas plus liquid coexisting. Why? Because at F, you have the condensation process which begins to take place. In other words, you're trying to convert gas to liquid. So in between, you have more gaseous molecules that are being converted into liquid molecules. That's why both gas and liquid coexist during this particular phase. So C is the best answer for us. Gas and liquid coexist between F and G. It's not liquid only because liquid only exists at G. Gas only exists at E. And solid and liquid cannot possibly be the answer because the solid is actually at point I. It's not part of this particular phase. So make sure you understand the differences between these changes of state. And for the heating curve, it is actually the opposite. So what you observe is that you have something like this, and then you have the change of state like this. So you're going to say this is solid at S, and then at S again, that is solid, and then it is going to go to liquid. So here you're going to have solid plus liquid, and the point when the conversion starts to gas, and this is the phase of the gas. So what is happening there is that the temperature increases from point 0 up to this point, and the temperature remains constant at this point because melting starts to take place. So here you have melting, and at this point you have all the solid converted to liquid. Again, the temperature here increases. In other words, it is being applied so that the particles can gain more kinetic energy so that they can be converted. So this temperature increases significantly up to point S. And at point S, then boiling starts to take place. This liquid is now converted to gas. That's why the temperature again remains constant. So this is the heating curve. You are increasing the temperature, whereas for the cooling curve, you are decreasing the temperature. For the heating curve, the purpose is to increase the kinetic energy of particles so that they can move rapidly. That's why you are increasing the temperature or the heat. For the cooling curve, you're trying to decrease that kinetic energy so that gases and liquids can be converted like that. So make sure you understand the differences. Question 8 says, the following diagram shows a water wave. Which row gives the correct values of the wave amplitude and wavelength? Well, when you're talking about waves, there are two types of waves that you want to be familiar with. You have transverse waves, and you also have longitudinal waves. In transverse waves, waves actually look like this. In longitudinal waves, waves actually look like this. Now, what is happening is that this is the resting position of a wave. So this is 0. Now, the maximum displacement of a wave from its resting position. Notice that this is the maximum displacement. That is what we call the amplitude. So in this case, the amplitude is actually from this point to that point. That is the amplitude of that wave. Now, one wave is actually the distance between the two crests or troughs. So from this position to this position, you have one wavelength. So make sure you understand that it involves the two displacements there. So for this question, as you can see, you can easily see the amplitude of this particular wave. Because it is the maximum displacement of a wave from its resting position, then you know that it is just from the resting position to the maximum displacement. Since this 8 centimeters is including the two displacements on both sides, then half of that is what we call the amplitude, because it is just from this position, which is half of 8, to the maximum point there. So the amplitude should actually be 4 centimeters. So we can eliminate answer choice C and D. Now for the wavelength, notice that the wavelength should be from this point to that point. Now for one trough here, notice that it is 5 centimeters, but this is just half of it. It is from this point to this point. To complete the wavelength, you have to extend it to the other point. And notice that these two are actually equal. They have to be equal. So this implies that even here you should have 5 centimeters. So the total value of this wavelength is going to be 5 plus 5, which is 10 centimeters. So 10 is the correct answer. We can eliminate answer choice B. And so our correct answer here has to be A. So make sure you understand how this is done. And if you're trying to calculate the speed of a wave, then that speed is actually given by speed is equal to frequency times the wavelength, which is lambda. And frequency is also given by 1 over period. So make sure you understand this. Now for longitudinal waves, what is happening here is that you have what we call compressions and rarefactions. This area is called compressions because notice that the particles are compressed together. They are closer to each other, whereby when you're talking about this part here, these are called rarefactions. The reason is they are widely spaced like that. So for longitudinal waves, they have that kind of a description. And not only that, another important point that you have to understand when you're comparing the two is that for transverse waves, the particles in a wave are actually moving perpendicular to the direction of travel of a wave. A wave is actually moving in this direction. Particles are moving in this perpendicular direction. That's why you have the maximum displacement at this point. So this is a wave. Notice that you have the movement of particles in this direction, which is perpendicular to the direction of travel of a wave. But for sound waves, particles actually move parallel to the direction of travel of a wave. So this is the direction of the wave, then particles also move in that particular direction. That's why you don't see these displacements in a longitudinal wave. And sound waves are examples of longitudinal waves. They are quite different from transverse waves. You have to know how you are distinguishing between the two. So make sure you understand that. Now this ties in with the next question, which is question 9. Question 9 is actually saying the diagram below shows a learner in front of a loudspeaker that produces sound. So keep in mind, sound is a longitudinal wave. So sound is actually longitudinal. Now, when you look at this diagram, it says which of the following diagrams best shows how the gaseous air molecules between the learner and the loudspeaker will move. Now, obviously, because sound is the longitudinal wave, then you know that the direction of the particles, in this case, the gaseous air molecules, is going to be parallel to the direction of travel of a wave. So, direction of a wave and this is direction of particles. So the direction of particles is going to be parallel to the direction of travel of a wave. So in this case, the loudspeaker is producing sound. Sound is moving in this direction so that the listener can actually hear it. The air molecules should also move in the same direction. The only addition we can make is that there is the classroom wall at this point, which means that sound can actually bounce back. And when it bounces back, it is going to move in this direction. So when you look at the choices here, actually A is the correct option here because this is showing that the gaseous air molecules are moving parallel to the direction of travel of this sound wave. And the two arrows are showing that one is going forward and then after it bounces back, it comes back to the direction it was coming from. So this is for transverse waves, so it can't be the correct answer. And this one is just one. So it can't be the correct answer because you have to have a reflection of sound or the bouncing back of this sound. Whereas this is just showing one direction of sound. And this is also incorrect because the direction of these particles is not actually parallel to the direction of travel of the wave. So make sure you understand the differences between transverse waves and longitudinal waves and examples. Water waves are transverse waves. Sound waves are longitudinal waves. Question 10. A girl of height 1.2 meters stands 4.0 meters in front of a plane mirror as shown in the following diagram. Now the question is, how far is the girl away from the image? What would you say? Now notice that you have a plane mirror. So this is the mirror that you have in your home, I guess. So when you stand in your mirror, what happens? Well, if this is the mirror, and you are standing in front of this mirror, let's say there's a distance of 2 meters between you and the mirror. You see yourself inside this mirror. When you see yourself inside this mirror, you have to understand that as long as this is a plane mirror, then the image that you see is actually a virtual image. Now, a virtual image is actually produced at the back of the mirror. So it is produced at the back and it is of the same distance as the distance of the real object from the mirror. So in other words, the distance between the image and the mirror is the same as the distance between the mirror and the object. So make sure you understand that if it is a plane mirror, then the image is actually virtual and it is produced at the back of the mirror and it has the same distance from the mirror as the object is from the mirror. So how far is the girl from her image? That's the key. It is from her image, not from the mirror. So the girl is, in this case, we have 4 meters. The girl is actually 4 meters from the mirror. But this means that the image is going to be produced at the back of the mirror. So let's make sure that so this is the girl, which means that the distance here is going to be the same as the distance between the mirror and the object. So it's going to be 4 centimeters. So how far is the girl from her image? This is from where she is to where the image is. So this distance is actually 4 meters plus 4 meters because the distance is actually the same. And so you're going to see that answer choice D is actually the correct answer. So it can't be C, 4 meters, because this is just from the object to the mirror. And it can't be 2.4 because there's no indication in this scenario that it can be. And it's not 1.2 because 1.2 meters is actually the height of the girl. So make sure you understand this. Question 11 says a line JK, which is here, drawn on a piece of plain paper on which a glass block is placed, was viewed through the top of its image and was located using a pin as shown in the following diagram. Now, if KL, which is the distance here, is 1.8 centimeters and km, which is from the top to the bottom, is 4.8 centimeters, what is the refractive index of the glass? What would you say? Now, the refractive index shows how the light of an object moves through the medium. In this case, what is happening is that a line is drawn at the bottom. So that is around J and K. So you draw a line on a plain paper. Then this is the glass block. So the glass block is actually transparent. You are trying to locate the position of that line which is drawn. And when you use a locating pin, it actually shows that this line which was drawn appears to be around L. Now this usually happens. You can have a cup of water and then you put some water in it and you put a spoon there. When you put a spoon there, you notice that when you try to look into the water, the spoon is going to look as if it is bending. So that is what is happening. This line which was drawn appears to be above, around L. The reason for that is because light is actually refracting as it moves from one medium to another. So you have the actual position of the image at the bottom. This is what we call the real depth. And you have where you see, or you seem to see, the position of that particular image at L. That is not the real depth, it is the apparent depth. So to find the refractive index, it is actually given by, so this is the refractive index. It is given by the real depth over the apparent depth. So in this case, what is the real depth? Notice that the real depth is from K to M, which in this case is actually 4.8 centimeters. So 4.8 centimeters is our real depth, and the apparent depth is actually from K to L. In this case, it is 1.8 centimeters from 4.8 centimeters, because keep in mind the eye is at the top. So it is the distance from where the eye is to where you are seeing the object from. So that is going to be 4.8 centimeters minus 1.8 centimeters. So that is going to be 3 centimeters. So that is going to be our apparent depth, 3 centimeters. And when you do the math there, you're going to get 1.6 as the refractive index. So answer choice C is the best answer. So make sure you understand the real depth, apparent depth in relation to the refractive index. Question 12 says, which of the following materials would be most suitable for constructing a core of an electromagnet? What would you say? Now, electromagnets are magnets that work under electricity. So what happens is that you can have something like a core, and then you use some coils, and then these coils are wrapped around the core. Then you allow electric current to actually pass through. And as this electric current passes through, it is able to create some magnetic fields. But because this core is used in electromagnets, what it does is that it simply magnifies the magnetic fields that are being produced by the coil due to the flow of electric current. So when that happens, you have what we call an electromagnet. It is a magnet that is operating under electric current. So these electromagnets are very important because they are used in things like watches, refrigerators, and so on. Something that you can turn on and off easily. And the good part about this is that the reason why they are used in such appliances is when you turn them off, or even in motors, when you turn them off, this core loses its magnetism. So when it loses its magnetism, then nothing works at that moment because you've turned everything off. You've turned the electric current off. Because remember that this magnetism only works when there is electric current which is flowing into it. When you turn the power on, then again, this core is magnetized. It increases the magnetic fields produced by electric current, and therefore the appliance continues to work on. So this is very important because let's say if you have something that does not lose its magnetism so easily, then even if you turn it off, it's still going to continue working, the thing which you don't want to happen. And also, if something that you use as the core here is something that is difficult to magnetize, then you can turn it on and still nothing is going to work because it is still not yet magnetized. So what you use for this core to make electromagnets is something that can be magnetized easily and something that can be demagnetized easily. When you are talking about electromagnets, iron is the most common substance that we use in electromagnets. The reason is because iron can be magnetized easily and also be demagnetized easily when electric current is turned on and off. And that's what you want. So iron is used for electromagnets in that particular case. Steel is hard. Iron is soft, that's why it is easily magnetized and easily demagnetized. Steel is actually hard, and so it is difficult to magnetize and it is difficult to demagnetize when it is magnetized. So you cannot use steel in electromagnets. Instead, you can use steel when you are making what we call permanent magnets. For iron, you can use it for temporary magnets. So just keep in mind, when you're dealing with electromagnets, iron is the best option for you. When you're using or trying to make the strong or permanent magnets, then you go for steel. Carbon and copper are non-magnetic materials, so they don't apply here. So make sure you understand how electromagnets work. Question 13 says, two uncharged metal spheres Q and P are placed on insulating stands and are separated while the negatively charged polythene strip is held near Q as shown in the diagram. Now, the question here is, what would be the charges on Q and P? What would you say? Now, this is static electricity. It is electricity at rest and it involves charges. What you need to understand is that there's what we call the law of electrostatics. What it means is that, or what it says is that, because you have only two charges, positive charges and negative charges, like charges repel each other. Unlike charges attract. So if you have two spheres, this one is positive, this one is negative, you see that there is a force of attraction that exists between them. But if you have a sphere like this and a sphere like that, and these are negatively charged, then you see the force of repulsion between them, so they repel each other. The same is true if you have positive charges like this, you again see the force of repulsion between them. Now, when you look at the question here, notice that the negatively charged polythene strip is negatively charged, right? So this is negatively charged. You don't know the charges of these two metal spheres, but because you don't know, you can assume that each sphere is having positive and negative charges. So positive charges, and also let's write negative charges like this. The same is true for the other sphere. So even for this one, you have positive charges in it and also the negative charges in it. So when you try to bring this polythene strip, which is negatively charged, nearby, What do you think is going to happen here in the first sphere, which is sphere Q? And this is sphere P. So these two spheres, Q and P, are uncharged. By that we mean that the number of positive charges and negative charges is equal in each sphere, and therefore they cancel each other. So they are uncharged, in other words, they are neutral. So when you bring this nearby, what is going to happen is that this negatively charged strip is going to repel the electrons or negatively charged particles in sphere Q. Now what is going to happen is, because these spheres actually are attached to each other, notice that they are attached to each other. So they are like this, and you have positive charges like that, and even electrons like that. So what is going to happen is that the negative charges are going to be repelled to sphere P. And when they are repelled to sphere P, because these are attached together, then the positive charges are also going to be attracted to this strip, which is negatively charged. So when the negatively charged particles move to sphere P, the positively charged particles in sphere P are also attracted toward this strip, which is negatively charged. So this is going to leave sphere Q with a net charge positive, and sphere P is going to be left with a net charge of negative. So this is going to be something that will look like this. So this is sphere Q, and this is sphere P. So what you see is that sphere Q is going to be like this, and sphere P is going to be like this. So the question is, what would be the charges on Q and P? Well, you can easily see that answer choice A is wrong, because you have both spheres positively charged. And let's try D. D is also wrong, because you have both spheres negatively charged. And C is also wrong, because the strip is near sphere Q, so it can't be negatively charged. So the correct answer here should be answer choice B. This is the only answer that shows what is going to happen when this negatively charged polyethylene strip is actually brought near these two uncharged metal spheres. So make sure you understand the principle under static electricity, how charges interact with each other, because it's going to help you deal with problems on static electricity. Question 14 says, the following diagram shows a network of 3 resistors R1, R2, R3 connected to a battery. Now, voltmeters V1, V2, and V3 are connected to resistor 1, resistor 2, and resistor 3 respectively. The question is, which of the following expressions show the potential difference supplied by the battery? What would you say? Well, since you are talking about the potential difference supplied by the battery, then obviously you are talking about the total potential difference. Now, the total potential difference, which is supplied by the battery, is the sum of the potential differences across the components in series. So if you want to find the total potential difference, which is the case here, it is the sum of all the potential differences across the components in series. Now, when you look at the resistors here, notice that resistor 1 is actually in series. Resistor 2 and 3 are in parallel. Now, when you look at these two resistors, resistor 2 and resistor 3, notice that voltmeter 2 and voltmeter 3 are connected to these resistors respectively. So the next principle that you want to understand is that the potential difference of the resistors connected in parallel is equal. The potential difference for resistors connected in parallel is actually equal. In other words, because R2 and R3 are in parallel, then it means that V2 is equal to V3. So as long as the resistors are in parallel, then the potential difference across those two parallel connections is actually equal. So if V2 and V3 is equal, and you have V1 which is connected to this resistor 1 in series, then what do you think is the total potential difference supplied by the battery? Well, on the surface, it will be like this is the total potential difference. So you're going to have V1 plus V2 plus V3. But notice that because we're dealing with these two resistors that are connected in parallel, then they are actually equal. If the resistors were in series, then we could write it like V1 plus V2 plus V3. But because these two resistors are in parallel, then V2 is equal to V3. So you cannot just write V1, V2, V3. In this case, you have to write just one of them. So you're going to have, in this case, because of the answers that we have here, we're going to write V3. So this is going to be our answer, and therefore answer choice A is the correct one. When you look at answer choice B, V2 plus V3 is not actually the total potential difference in this particular case, which is supplied by the battery. That will be the potential difference in parallel between the two resistors. And C is also not correct because it assumes that V1, V2, and V3 are all in series connection. Whereas in this case, we see that V2 and V3 are actually in parallel connection. So that can't be the answer. And D is also incorrect because it's trying to subtract V2 plus V3 from V1, which is not the case here. So make sure you understand that when you're dealing with resistors connected in parallel, then the potential difference is actually the same across all resistors. When you're dealing with resistors connected in series, then the potential difference is actually different. Now, the next question, which is question 15, actually says an electric kettle is rated 230 volts and 3000 watts. What is the suitable fuse to use on this kettle? What would you say? Now, a fuse actually acts like the sacrifice of an electrical appliance because it controls how much of the current should actually come inside this electric appliance. So what happens is, if you have, let's say, a kettle, so this kettle is supplied with the current of, let's say, 10 amps. This means that when you have a fuse in this particular kettle, it should be rated slightly above this current which is being supplied to the kettle. So it should be maybe 12 amps. The reason for this is sometimes this current may go up, maybe up to, let's say, 15. Because sometimes it happens like that. So instead of this current destroying the kettle, it actually destroys the fuse. So the fuse acts like a sacrifice. It sacrifices itself at the expense of this entire electrical appliance. And when it is destroyed, you can actually replace it. So that's how the fuse operates. So make sure you understand that the rating of the fuse has to be slightly above the actual current that is flowing into the electrical appliance. So with that in mind, what we have to do is, since we are looking at the rating of the fuse, then we have the voltage and also the power. So we can go ahead and calculate the current. So current is going to be given by power over voltage. And in this case, current is going to be, what is the power here? Notice that it is 3000 watts. And the voltage is actually 230 volts. So the current is going to be, this is going to be 13.04 amps. So this is the current flowing into the electric kettle that we have, because these are the ratings that we have. So this means that if this is the current that is flowing into the kettle, what is the suitable fuse to use on this kettle? Remember that the rating of the fuse should be slightly higher than the current that is flowing into the electrical appliance, so that should this go up, the fuse is going to be destroyed instead of the electrical appliance itself. So when you look at the options here, notice that you can't go for option A because it's just too little. Remember that the rating of the fuse should be slightly above what we've calculated, which is 13.04 amps. So option A, option B, and option C can't be correct. And the only correct answer there is actually option D, because this 15 amps is slightly above what we have here. And so that's how we deal with such problems. The next question, which is question 16, says below are 3 statements on electromagnetism. So we come back to electromagnets. Which of the above statements are true? Let's look at the first statement. It says an electromagnet consists of a coil of wire wound on a soft iron core. Is that statement true or false? What would you say? Well, the first statement is actually true. The reason is electromagnets, as already pointed out, uses the soft iron core because it is easily magnetized and easily demagnetized. Remember the use of electromagnets in some appliances like motors or some watches. You have to turn these appliances on and off. That requires what we call electromagnetism. And iron core, soft iron core, is actually the best material or substance that you can use when you're trying to use or make electromagnets. So the first statement is actually true. What about the second statement? It says the strength of the magnetic field produced by an electromagnet increases if the strength of the current and or the number of turns of wire is increased. Now, this statement is also true. The reason why that is true is if you have the iron core like this and you have the turns like that, remember that this electric current which passes through is able to produce magnetic fields along the coils themselves. And this iron core is going to increase those magnetic fields. But if you increase the current, then it means that you've increased the strength of magnetic fields, which means that the same is true if you increase the number of turns, the number of coils, then you've increased the magnetic field. So this statement is true because it is talking about the strength of magnetic fields. This strength of magnetic fields is going to be increased when you either increase the current or you increase the number of turns of the wire. So that statement is actually true. Now, what about the third statement? What would you say? The third statement says in the diagram below, when the switch is closed, the gap R, which is here, is going to increase. Is that true or false? What would you say? Well, let's test this. The first thing that you wanna understand here is that notice that this is the battery. Now, when you have a battery like that, you have to understand that current flows from positive to negative. That is electric current. It flows from the positive terminal of the battery to the negative. When you're talking about the flow of electrons, electrons actually move from negative to positive. So that's the difference that you need to understand. Now, the other thing is that when you're looking at the terminal, the longer terminal is actually a positive terminal. In this case, the left terminal here is positive. The right terminal is actually negative because it is shorter. So that's the second thing that you need to understand. So this means that current is going to move from the left side to the right. So it is going to move in this direction. And when it moves along the coils, it's going to move like this, like this, like this, like this. Now, at this stage, because you want to know whether the gap at R is going to increase or decrease, or you want to test this statement, whether it is true or false. When you reach this stage, there is actually what we call the right hand grip rule. This right hand grip rule is used to determine the poles of the magnet and the direction of magnetic fields. So what it states is that you can use your fingers of your right hand in the same direction of the magnetic field, and then the thumb is going to be stretched. The direction it is going to point is the direction of the magnetic field, which is going to be a north pole. So this is going to be like this. So this is going to be your thumb. So your thumb is going to be like this. And here you're going to have your fingers. So this is your right hand. And when you look at your right hand, so these are your fingers. Just make sure that we draw this at least with some clarity. So this is going to be like this, and this is going to be like this, and then you have this. So this is the right hand grip rule. What happens is that these fingers are showing the direction of the current itself as it flows through the coils. So notice that when you compare this right hand with what we have here, you can see that the direction of current is similar. As current flows through the coils, so this hand is showing that these are the coils, so to speak. So current is moving in this direction. So this thumb then is moving in this direction. And the principle is the direction of your thumb is actually going to produce a north pole. So with this, we can understand that the left end of this electromagnet is going to be the north pole because that's the direction, and the right end is actually going to be the south pole. So what happens here is that because this is the north pole and this is the south pole, remember the law of magnetism, which states that like poles repel, unlike poles attract. So since you have south and north, which are unlike poles, then you are going to see some attraction between these two. So this means that this is a false statement. The distance here is going to decrease because these two are going to attract each other. If the case was that the pole at this particular point is actually the south pole, then this statement would have been correct because the unlike poles repel each other, so the distance would have increased here. But based on this principle, the statement is actually false. So only the two statements are correct, that is 1 and 2. So answer choice A is actually the correct one. So make sure you understand how the right hand grip rule is used to determine the magnetic field, the direction of the magnetic field, and also the direction of current. The next question says, the diagram below shows a filament lamp rated 6.0 volts connected to the output of a transformer. Now the question is, what happens to the lamp when the circuit is switched on? What would you say? Well, first of all, it says that this filament lamp is rated 6.0 volts. So since it is connected to the output transformer, and this is the filament here, well, you have to know the amount of voltage arriving at the filament lamp here. So how do you calculate the voltage at that particular point? Well, this is the transformer. Whenever you want to calculate either the voltage or the number of turns in the coil, you want to use this formula. So you have secondary voltage over the primary voltage, which is equal to the number of turns in the secondary circuit over the number of turns in the primary circuit. So this is what you're going to have. And this is the secondary circuit connection of the transformer. So when you look at that, you're going to see that this is going to be Vs, which is secondary voltage. In this case, it is 240. And the primary voltage is what we are looking for. So this is Vp. So this is going to be Vp. And the number of turns in the secondary circuit is actually 300. So this is 300 turns. And the number of turns in the primary circuit is actually 20. So we're going to have 20 turns there. So this is going to give us 300 Vp is equal to 240 by 20. 240 by 20. And here we are going to divide by 300 by 300. So the voltage in the primary circuit is actually going to be 16 volts. Now, when you look at 16 volts, notice that it is way higher as compared to what this filament lamp is rated, because it is rated 6.0 amps. This is way too below this particular voltage that is arriving at the filament lamp. So because it is too much, the first thing that you want to observe is that the filament lamp is going to be brighter, but because this is too much, then it is going to go out. It is going to blow off. So in this case, you can see that answer choice D is the correct one. The filament lamp lights up brightly because the current that is arriving at it is actually too much, and then it blows off. So that's what is going to happen because it cannot endure that much voltage that is arriving at it. So it can't be lighting with normal brightness, and you can't say that it doesn't light at all or that it lights dimly, because that does not fit the description of what we are seeing here. So make sure you understand especially how to calculate the number of turns in the primary and secondary circuit connection of the transformer, and also the voltage. This formula is going to help you deal with such problems. Now the next question is, which component used in electronic circuits allows current to flow through in one direction only? Well, the correct answer here is answer choice A. A diode is a component that allows current to flow through in one direction only. When you're talking about resistors, these allow current to flow in both directions. The same is true for thermistor. The same is true for the transformer, because the transformer transfers energy via magnetic field and it doesn't allow or block current direction. So make sure you understand that when you're talking about the flow of current in one direction only, then the diode is actually the component that you want to go for. Question 19 says an atom of uranium-235 has 92 electrons. How many protons are there in one atom of uranium-235? What would you say? Well, this uranium atom is actually a neutral atom. So uranium is a neutral atom. Now, why is it a neutral atom? Well, let's give an example. Let's say we have sodium. Now, the atomic number for sodium is actually 11. When you try to write the electronic configuration of sodium, it's going to give you 2, 8, 1. Now, in this case, sodium is unstable because it has 1 electron in its outermost shell. It needs to have 8 electrons for it to be stable. So what should be done? Which one is more convenient? Losing this electron so that it remains with 8, or looking for 7 more electrons so that this one becomes 8? What would you say? Well, it's more convenient to just lose this electron. And when it loses that electron, it remains stable. But then what happens is that the principle is that the number of protons is equal to the number of electrons. Protons are positively charged particles inside the nucleus of an atom. Electrons are in the shells, and these are negatively charged. Now, the number of protons and the number of electrons is actually equal. So this means that when you have uranium like this, then obviously because it has 92 electrons, then it should have 92 protons, because the number of protons and the number of electrons must be equal. So that's the correct answer for that particular question. So just understand that when you're talking about atoms, they have the same number of protons and electrons. If it is an ion in the case of sodium, then after losing that one, you see that the proton number remains 11, whereas this electron number is going to remain 10. And you are going to, the number of electrons, because these are negatively charged and the protons are positively charged, then the 10 negatively charged electrons are going to cancel the 10 positively charged protons. So you're going to remain with 1 proton, which is going to define the charge of this particular atom, which is sodium. So that's how sodium becomes an ion. It actually loses 1 electron and then it becomes an ion. So that's how you form ions. So when you're talking about uranium 235 having 92 electrons, then it must have 92 protons by the same principle. So that's how this works. Okay, so we can look at this one last question on these multiple choice questions, which is question 20. So it says a radioactive material gives a count of 8,000 counts per minute. After 20 days, it gives a count rate of 500 counts per minute. What is the half-life of the material? What would you say? Now, when you're talking about the half-life is the time it takes for a substance or the mass of the substance to decrease by half. Let's say you have something that has the mass of, let's say, 20 grams. 2 days later, this mass decreases to 10 grams. So it means that the half-life of this particular substance is actually 2 days, because it takes 2 days to bring this initial mass of a substance to half, which is 10 grams. So that is what we mean when we say the half-life of something. Now, in this case, notice that you have the initial count rate. So you have the initial count rate of 8,000 counts. Now, this 8,000 counts is actually measured using the Gigamolar counter. But it says after 20 days, the count rate that you have is actually 500 counts per minute. So what has happened? It has dropped from 8,000 counts per minute to 5,000 counts per minute. So what is happening here? Well, what is happening is, since you understand what the half-life is, you have 8,000 counts initially. When 8,000 counts decrease by half, you have 4,000 counts, because half of 8,000 is actually 4,000. Then when this decreases further by half, it is going to give you 2,000 counts. When this decreases further, it is going to give you 1,000 counts. And when this decreases further, it is going to give you 500 counts. So it dropped from 8,000 counts to 500 counts in this case. So this is what is happening. So this is the first half-life, this is the second half-life, this is the third half-life, and this is the fourth half-life. So for it to move from 8,000 all the way to 500 counts, notice that you have 4 half-lives that have passed through to just decrease the mass of this particular substance from 8,000 to 500. So that's the first point that we need to understand. You have 4 half-lives. So 4 half-lives. Now, what we are trying to determine is the half-life of this material. Not for 4 half-lives, but for 1 half-life. So what are we going to do here? Notice that the entire time it takes for this material to decrease from 8,000 is actually 20 days. So this 20 days is for 4 half-lives to decrease it from 8,000 to 500. So for us to find the half-life of, or the value of 1 half-life, for us to find the value of 1 half-life, we just simply need to divide 20 days, which we have, over the number of half-lives that we have. So this is going to give us 5 days. So as you can see, this is not difficult to find. When you look at answer choice B, that's the correct answer, because it shows that 5 days is the half-life, the time it takes to move from 8,000 to 4,000, and then from 4,000 to 2,000, and then from 2,000 to 1,000, and then from 1,000 to 500. All these other choices are not actually correct. So make sure you understand how half-life actually works when it comes to atomic physics. Now that we are done with multiple choice questions, let's go ahead and deal with section B. Now, section B1 says, the figure below, which is figure B1.1, shows a simple pendulum suspended from a fixed point. Now, the bulb is slightly pulled to position A and then released. The first question is, state one factor that does not affect the period of the pendulum. Now, the period of the pendulum, you must remember, is the time taken for this bulb to make one complete oscillation. Now, this means that if you have a fixed point like this, and you have a pendulum bulb like this, so let's say this is position A, this is B, and this is C. So for you to make one complete oscillation, it means that if this is the resting position, which is B, the period of a pendulum means that you have to push this bulb to position A and then release it. When you release it, it is going to pass through B to C, and then it is going to come back to the resting position again. So the time it takes for this bulb to move from A to C and then back to A is what we call the period of the pendulum. So make sure you understand that. Now, when you are talking about the period of the pendulum, the period is actually given by the formula T, which is the period, and this is going to be 2 pi, and we are going to have the square root of gravity. So this is the formula for the period of a pendulum. Now you will notice that gravity can affect the period of the pendulum. So this gravity is actually acceleration due to gravity. And the L here is actually the length. So you can see that length and the acceleration due to gravity, these are going to affect the period of the pendulum because they are part of the formula. The only factor here that is not going to affect the pendulum is actually the mass. Mass is not going to affect anything because whether the pendulum has larger mass or smaller mass, it's not going to affect this because mass is not even part of the equation. So make sure you understand that the bulb may have maybe 20 grams or even 50 grams. That is not going to affect anything. So in this case, we can just write mass as one factor that does not affect the period of the pendulum. But also even the amplitude itself for small angles is not going to affect the period of the pendulum. But we can just write mass like that as our answer. Now, question B says, if the values of time for 20 oscillations obtained were, then you have all these values, 16.1 seconds, 15.9 seconds, 16.0 seconds, 16.2 seconds, and 15.8 seconds. Calculate the period of the pendulum. Now, remember that when we are talking about the period of the pendulum, we are simply talking about the time it takes to make one complete oscillation. So, since we have these values, the first thing that we need to understand is we can actually find the average of the time that we have. So if we find the average here, we are going to get 16.1 plus 15.9 plus 16.0 plus 16.2 plus, and then this is 15.8 over 1, 2, 3, 4, 5. So we're going to divide by 5. So this is going to give us the average of 16 seconds. So this is our time. In other words, it takes 16 seconds to make 20 complete oscillations. So here we have 20 oscillations and this is our time. The average of this is actually 16 seconds. So that is our time now. Now to find the period of the pendulum, remember that it is the time it takes for a bulb to make one complete oscillation. Now for 16 seconds, how many oscillations are made? Notice that we have 20 oscillations. So 20 oscillations for 16 seconds. What happens if we want to find just the time for one oscillation? We have 20 oscillations. What about the time for just one oscillation? Well, the period then is going to be simply dividing 16 seconds by the number of oscillations. Then we're going to get the period for one oscillation. So we're going to do 16.0 seconds over 20 oscillations. And when we do that, we are going to get 0.8 seconds as our period. So this is the period of the pendulum. So here we can write 0.8 seconds as the period of the pendulum. So make sure you understand the question because it is talking about the period of the pendulum. Since you have 20 oscillations and the time is given, just find the average of that time and then divide that time by the number of oscillations to get the period of the pendulum. Now, the last question is actually calculate the frequency of the pendulum. So how do you go about calculating the frequency of the pendulum? Now, frequency is simply the number of oscillations made in 1 second. You can calculate the number of oscillations made in 1 second, but typically we use this formula to calculate the frequency. So it is simply frequency is equal to 1 over period of the pendulum. But since we have the value of t here, then we can go ahead and find the frequency. So the frequency is going to be 1 over, our period of a pendulum is actually 0.8 seconds. So our frequency is going to be 1 over 0.8 seconds is going to give us 1.25 hertz. So this is our frequency. So make sure you understand how to deal with problems on the period of the pendulum. You might be asked such questions repeatedly. Just know how to answer them, and also make sure you get used to know the formulas, because they are going to help you deal with problems on the period of pendulum. Question B2 says, a car has a mass of 900 kg. It accelerates from rest at the rate of 1.2 meters per second squared. So that's the acceleration. Now the question is, calculate the time taken to reach the velocity of 30 meters per second. What would you say? Now notice that we are calculating time, and we have the acceleration and also the velocity. Now acceleration is the rate of change of velocity with time. So it is actually given by acceleration is equal to final velocity minus initial velocity over time. Notice that we are finding time, so we are looking for the value of t. Now, since we have 30 meters per second, notice that it says that the time it is taken to reach this 30 meters per second. So this is actually the final velocity. This is the value of b. For the initial velocity, this car started from rest. So the initial velocity has to be 0 meters per second. So let's go ahead and plug in these values, because we have the acceleration of 1.2 meters per second squared. So we are going to say 1.2 meters per second squared for acceleration. And then this is going to be, final velocity is actually 30 meters per second. The initial velocity is 0 meters per second. And we are looking for time. So this is going to be over 1. So we're going to have 1.2 t is equal to 30 as our number on the right side. So to find the value of t, we can reduce by 1.2, 1.2. And so this will cancel. T is going to be 30 over 1.2 is actually 25 seconds. So this is our time. The time here should be 25 seconds. So make sure you understand how to deal with these problems. For acceleration, it is the rate of change of velocity with time. So this is the standard formula that we use. You can just change the values depending on what you've been given, and so for whatever you've been asked to solve. Now, question 2 says, calculate the force required to accelerate the car at the rate of 1.2 meters per second. So how do you calculate the force? Now, for you to calculate the force, you have to link that acceleration to force. So the formula that links acceleration and force is actually force is equal to mass times acceleration. This is the standard formula that connects force to acceleration. So in this case, we can go ahead and find the force using that particular formula. Because for a car to actually make a movement, force has to be applied. Force is the pull or push that is done on an object. Acceleration is the rate of change of velocity with time. So for a car to accelerate, it has to be pushed with some force. So how do we find that force? We use this formula. So let's go ahead and find the value of force. Notice that here we need to have mass, and fortunately we have the value of mass here, which is 900 kg. So we are going to use that 900 kg and multiply it by the acceleration that we have, which is 1.2 meters per second squared. So this is kg, and then we are going to say force is equal to, what is 900 kg multiplied by 1.2 meters per second of acceleration? Well, we are going to get 1080 newtons. So this is our force, and remember that force is actually measured in newtons, acceleration in meters per second squared, while velocity is simply in meters per second. So the force here is going to be 1080 newtons. So make sure you understand how to connect force with acceleration and how to deal with problems on force. Question B3 says, figure B 3.1 below is a diagram showing a load being moved using a wheelbarrow. Now, this is the figure B 3.1. It says the total mass of the wheelbarrow and the load is 80 kg. And the gravity is actually 10 newtons per kg. So the first question is calculate the weight of the wheelbarrow and the load. So how do you deal with this problem? Now, when you're talking about weight, you have to understand that you're dealing with things that are in the vertical position. If you lift something, the force of gravity is actually exerted on that particular object, pulling it downwards. So that is actually what we call weight. However, when you're trying to pull something in the horizontal position, what you are applying is actually force. So you're applying force in the horizontal position, whereas when you're dealing with things in the vertical position, for the most part, you're dealing with weight. Now, when you're looking at force, the formula for force you must remember is actually force is equal to mass times acceleration. Now, this acceleration can actually be acceleration due to gravity if you are dealing with the vertical objects. So weight is essentially the same formula that we use for force, except that because we are dealing with acceleration due to gravity, then we are going to use G instead of A. So make sure you understand that. Now, when you are pushing something, let's say you are pushing this object, which is object A. When you are pushing it in this direction, what you are using is actually what we call the effort. So the effort is actually the type of force that you're applying to an object. But there's also the resistant force that is exerted by this particular object. And this resistant force, which is in the opposite direction to the direction of the applied force, is actually what we call the load. So this load has to be overpowered by the effort. So make sure you understand these two principles as well. So let's go ahead and see how we can find the value of weight in this particular case. Now, when you look at this wheelbarrow, notice that there is this upward force which you've used, which is the effort to lift this wheelbarrow. So the arrow is pointing upwards because you're trying to lift it. This is the load. In other words, it's something that you need to overcome by applying that effort or force that you're applying upwards. When you're looking at the weight is equal to mass times the acceleration due to gravity. So in this case, you will realize that the mass of the wheelbarrow and the load itself is actually 80 kg. So that is our mass. So we are going to say weight is going to be given by the mass that we have, which is 80 kg times, notice we have the acceleration due to gravity here, which is 10 newtons per kg. So this is our acceleration due to gravity. So we're going to say this is multiplied by 10 newtons per kg. So weight is going to be equal to 80 kg times 10 newtons per kg is going to give us 800 newtons. So that is our weight. That is the weight that we can find for the wheelbarrow. So we are going to say the weight here is actually 800 newtons. Now the next question is calculate also the force. This is F required to lift the wheelbarrow. So that is the effort that you are trying to find. So how do you find this particular force? Now, for you to lift this wheelbarrow, notice that there is a pivot here in the wheel of the wheelbarrow. The way you are going to lift the wheelbarrow is also dependent on the friction in the wheel of the wheelbarrow. And the distance between this wheelbarrow, which is the pivot in this particular case, and the distance or the region where the force is being applied is actually perpendicular to the direction of the force itself. So this distance is perpendicular to the force applied. And this creates what we call the moment of force. So when you are looking at the moment of force, again, remember the moment of force is actually the force applied times the perpendicular distance. But on top of that, you're going to realize that this wheelbarrow has this weight, which we found to be 800 newtons. So this means that there are two active forces here. There is the weight, which is pulling downwards, and there is this force, which is pulling upwards. So in this case, you have two forces that are being exerted on this entire thing. But the pivot still remains at the wheel axle, which is here. So this is the pivot. So what we are going to discover is that there is the first force from the pivot, and this is having the distance of 0.5 meters. And there is the second force here, which is having the distance of 1.5 meters and 0.5 meters from the pivot, because the pivot is the main position or the main reference point that we can refer to. So in this case, because we have two forces and those distances, what we have here is what we call the principle of moments. And remember, the principle of moments states that the sum of the clockwise moments must be equal to the sum of the anti-clockwise moments. So when we look at the clockwise moments, what we are going to discover is that we have moment of force for the clockwise moment and moment of force for the anti-clockwise moment. So what we are going to do is, for the clockwise, what we have is the weight and the distance from the pivot. So the weight here is actually 800 newtons times the distance is actually 0.5 meters. And for the anti-clockwise, we have the force that we are looking for times the distance, which is 1.5 plus 0.5. So that is actually 2 meters. So we can go ahead and solve for F. So here, 800 times 0.5 is essentially 800 over 2, which is going to give us 400. And here we're going to have 2F. So over 2 over 2. The value of F here is going to be 200 newtons. So this is our force. This is the force that we have here. So that is our answer. So force is going to be 200 newtons. So make sure you know how to deal with these problems, especially on the moment of force and also regarding force itself, acceleration, and so on. And make sure you pay attention to the formulas, the units, and how to solve the problems. Now, question B says, state whether force F would increase or reduce when the handles of the wheelbarrow are made longer. So what do you think is going to happen to the effort, the force F, when the handles of the wheelbarrow are made longer? Well, just try to think about this. Remember that according to the principle of moments, the sum of the clockwise moment must be equal to the sum of the anticlockwise moment. Now, what happens if you increase the distance between this point, which is W, and this particular point? Well, it means that on this side, the distance is going to change. It is going to increase. Now, what we have initially is that here we have the force of 800 newtons and the distance of 0.5. Whereas here we have the force of 200 newtons times the distance of 2 meters. Now, in this case, when you multiply this 800 times 0.5, you're going to get 400. Even here, 200 times 2 is going to give you 400. So this obeys the principle of moment. The sum of the clockwise moment must be equal to the sum of the anticlockwise moment. Now, what happens when you increase this distance here? So when you increase the distance, let's say the handle is actually made longer by some meters. So let's say this moves from 1.5, which is here. From 1.5, this moves to 2.5. When it moves to 2.5, it means that the total distance that you're going to have is 2.5 plus 0.5, which is actually going to be 3 meters. So make sure you understand that when we try to multiply this is going to give us 200 times 3, which is 600. Here we are going to remain with 400. So this does not obey the principle of moments because it is larger on this side than on the other. So in order to obey the principle of moments, when the distance is increased like this, what should you do to make sure that it is still balanced, to make sure that it remains 400? Well, in that case, you have to decrease the amount of weight that you have, the amount of force, the amount of effort. So this force is going to decrease from 200 to actually 133.3. The reason is you want to make sure that you remain with the same thing here. So here we are going to have 800 times 0.5. When you multiply this, you are still going to get 400 approximately. And when you multiply this, you're going to get 400. So it still obeys the moment of force or the principle of moments. But keep in mind, the force F is reduced. In other words, the longer the handles, the less force you're going to apply. You can just make an experiment. When you get the wheelbarrow and then you use longer handles, you're going to see that you apply less effort. Whereas when you use short handles, you're going to apply a little bit more of the force. So this is what is going to happen in this case. When you look at the question here, state whether force F would increase or reduce when the handles of the wheelbarrow are made longer. So you can clearly see that this force is going to reduce. So that is our answer. So make sure you understand these points. Now, question B4 says figure B 4.1 below is the diagram showing a stone of mass 2 kg that was pushed up a slope from Q to R. So this is the starting point. It was pushed from Q all the way up to where it is at point R. Now, the statement says 72 joules of work was done in moving the stone up the slope from Q to R. So the work done was actually 72 joules. Now the question is, what is the potential energy of the stone at R? What would you say? Now, what happens here is that the work done in moving the stone up the slope is actually converted into the gravitational potential energy at this particular position at the top. So that is what is going to happen. You are using 72 joules of work to push this stone upwards all the way up to this position, that work that you've applied is actually going to be converted into gravitational potential energy at this time. So as you are trying to lift or move this particular stone, that work of 72 joules is actually being converted gradually until when the stone is at its resting position at the top, that work is completely converted to gravitational potential energy. So when you're talking about the potential energy of the stone at Ara, just know that this work that was used is actually converted to the potential energy that you need for the stone at Ara. So the potential energy is going to be 72 joules. Now, the second question is, if the stone falls through the side RT, so this is the side, what would its potential energy be at S? This is the midpoint of its fall. So what would you say? Potential energy is given by mass times gravity times height. Now, when you look at this particular formula, and remember that potential energy is the energy possessed by an object at its resting position. So this potential energy and the height are directly proportional. In other words, if you increase the height, you increase the potential energy. Conversely, when you decrease the height, you decrease the potential energy, because height is directly proportional to potential energy. And here we are dealing with the height. Now, as the stone starts to fall, you must remember that it starts to lose its energy to kinetic energy. Because it is moving, the energy possessed by an object when it is moving is actually the kinetic energy. So there is the net conversion of energy from potential energy, gravitational potential energy, to the kinetic energy. But here at S, you are going to discover that since the gravitational potential energy at the top is actually 72 joules, then by the time it reaches S, which is the midpoint, the fact that the height is directly proportional to the potential energy shows that by the time it reaches point S, then this potential energy, which is the gravitational potential energy, is going to decrease by half, because this is the half. Let's just imagine that this is 10 meters. So this is 10 meters. If that is 10 meters, then at point S, you have 5 meters, which means that the potential energy at that point is simply going to be the same mass times gravity times height, but this is going to be over 2. Why? Because it is half of the distance. This 2 is reducing this height by 2. So because of that, this potential energy is going to decrease by half. So essentially, the potential energy we know is 72 joules. So this is going to decrease by half because it is the midpoint. And then that is going to give us 36 joules. So 36 is actually the potential energy at point S. So we are going to have 36 joules. So make sure you understand, because potential energy is directly proportional to the height. So when you reduce the height to this position, which is the midpoint, then the potential energy also decreases by half. Hence, it moves from 72 to 36 joules. Now, question C says that calculate the height RT. So how do you find the height RT? Well, because you have the potential energy, for this particular question, you still need to use the same formula, which is mass times gravity times height. So we are looking for the height. Now, the potential energy is actually 72. So we are going to put 72. And the mass of this stone is actually 2 kg. Notice we've been given 2 kg there. So it is 2 times Now the acceleration due to gravity is still 10, and we have the height. So this is going to be 72 is equal to 20h. And so we can solve for h by dividing by 20. So h is going to be 3.6 meters. So that is our height. So the height here is actually 3.6 meters. Now the last question is actually saying find or calculate the velocity of the stone just before it strikes the ground. So this means that when you look at the diagram, when this stone falls in this direction, just before it hits the ground, find the velocity of that particular stone. So how do you find that velocity? Well, the thing is, remember that the energy possessed by an object when it is resting is actually the potential energy. In this case, this stone is having gravitational potential energy. And remember that when it reaches this point, it is actually reduced to half, which means that when it passes this particular point S, it continues to decrease. But as it decreases, where is the energy going? Again, remember the law of the conservation of energy. Energy can neither be created nor destroyed. Rather, it is converted from one form to another. In this case, because the stone is moving, potential energy is being converted to the kinetic energy. By the time the stone completely hits the ground, the entirety of this potential energy is converted to the kinetic energy. But just before it hits the ground, the principle is that the potential energy equals the kinetic energy at that particular point. And this is what you're going to use to solve for velocity of the stone at that particular point. So how are you going to do that? Well, since you have the potential energy, which is 72, you're going to write 72, and you're going to replace kinetic energy with its formula. Kinetic energy is actually given by half mass times velocity squared. So you can go ahead and replace where there is kinetic energy, you put its formula. So we're going to write half mass times velocity squared. So at this time, all you have to do is we can write half mv squared on this side to make our calculation easier. Now, what is the mass of this particular stone? Because where there is m, we can replace it with mass. So our m there is actually 2, and this is going to be v squared is equal to 72. Now you can cancel 2 here. You're going to remain with v squared is equal to 72. So you can introduce the square root here to solve for v. So v is equal to, the square root of 72 is actually 8.49. And since this is the velocity, this is in meters per second. So this is the velocity of the stone just before it hits the ground. So make sure you understand these principles. They are going to help you when you're trying to deal with problems on energy, work, and power. Question B5 says, figure B5.1 below is a diagram showing a wave traveling along a spring in the direction. So here's the figure. And the first question is, in what way is the wave the same as the sound wave? What would you say? Well, remember that when you're dealing with waves, you have two types. You have transverse waves and longitudinal waves. When you're talking about transverse waves, they look like this. This is the direction of the wave, but the particles actually move perpendicular to the direction of travel of a wave. For longitudinal waves, you have these compressed sections called compressions. You have these dispersed sections called rarefactions. So again, you have compressions and rarefactions like that. So which of the two waves resembles this particular wave that we have in the diagram? Well, you know that this is clearly pointing to this particular wave, which is the longitudinal wave. So in what way is this wave the same as a sound wave? Well, just know that it is longitudinal. They are both longitudinal waves. So you can write they are both longitudinal waves. So make sure you understand that. Now, keep in mind that the direction of the particles in a transverse wave is perpendicular to the direction of travel of a wave. Whereas in longitudinal waves, the particles move in the same direction as the direction of the wave itself. And since I've pointed out, as you've heard, that the particles move in transverse waves perpendicular to the direction of travel of waves, while in longitudinal waves in the same direction, it shows that these waves are being made by particles themselves. For example, sound waves, they travel in a medium. Sound waves cannot be produced in a vacuum because these waves are dependent on the material. So they can pass through solids, liquids, and gases. Because these particles, when they receive energy, they vibrate more and transfer the same energy to the next particles, and therefore the sound wave is actually created like that. So the second question, which is question B here, is saying, what are the regions U and W? What would you say? Well, I've just said that these that are compressed together are called compressions. So you have compressions, and these that are widely spaced are actually called rarefactions. So these are rarefactions. So make sure you understand that. For transverse waves, you have crests and troughs. Whereas in longitudinal waves, you have compressions and rarefactions. So make sure you know the differences. Now, question C says, explain why sound waves travel faster in liquids than in gases. Well, when you look at the arrangement of particles in liquids and gases, actually, let's write solids. So this is solid. So we're going to say particles are arranged in this manner. When you're looking at liquid, particles are arranged in this manner. And when you look at the gas, particles are arranged in this manner. So sound travels when particles vibrate. They try to pass on that sound energy to the neighboring particles, and the neighboring particles pass on that energy through vibrations to the neighboring particles, and that's how sound is transferred. So when you look at these three states of matter, you realize that in solids, sound travels much faster than in liquids, and sound in liquids travels much faster than in gases. The reason is when the sound energy reaches the particles, they are able to vibrate. And as they vibrate, because they are closely packed, then they pass on that sound energy to the next particles, which then pass on to the next particles, and which then pass on to the next particles. So sound travels much faster in solids. Now, in liquids, the same happens. Because they are not widely packed, still the particles are able to transfer the sound energy to the neighboring particles. The reason why in gases sound is very difficult to travel, or rather it travels much slower, is because the particles are widely spaced. for this particle to transfer the sound energy to the next particle, it will require some effort because they are not closely packed. So it is for that reason that sound travels much faster in liquids than in gases. So make sure you understand that, because you might be given, let's say, steel and let's say water, and they tell you or ask you to state which material is going to transfer sound at a faster rate. So you know that in solids, sound is going to be much faster. It is going to travel much faster than in liquids and gases. Particles in liquids are closer together than in gases. Hence, sound travels much faster. So make sure you understand these points. Now, question B6 says a ray of light travels from air into water at an angle of 40 degrees between the normal and the incident ray. If this ray produces an angle of refraction of 29 degrees, calculate the refractive index of water. Now, when light is traveling from air to water, it travels like this, and then as it enters into the second medium, it is going to bend in this way. Now, this is going to be the normal. So this is the normal ray. The ray that is coming from the source of light is actually going to be the incident ray. And the one that is in the second medium, that is refracted, is actually called the refracted ray. Now, the angle between the normal and the incident is actually what we call the incident angle. So this angle here, which according to the information given, it is an angle of 40 degrees because it is between the normal and the incident ray. So this is going to be 40 degrees. Now, the ray produces an angle of refraction of 29 degrees. So the angle of refraction is actually the angle between the normal and the refracted ray. So this is going to be 29 degrees. So this is the information that we have. Now, the first question is find the refractive index of water. Now, the refractive index is actually sorted out or found using what we call the Snell's law. Now, this Snell's law is given by N1 sine theta 1 is equal to N2 times sine theta 2. Now, N is the symbol of the refractive index. So it is given by N. And in this case, since we are dealing with the two mediums, notice that this is the air medium, this is the water medium. So the refractive index of light in the air and the refractive index of light in the water is actually different. But usually, this N, which is representing the refractive index of air, is actually 1. So the refractive index of the light in the air is actually 1. So we can neglect that one and go ahead and solve for the refractive index, which is N here. So this is going to give us, if we make this N the subject of the formula, this is what we are going to have. So we are going to have the refractive index, so we're just going to write N, and we're going to have sine theta 1, which is the angle of incidence. So the angle of incidence, which is in this area, in the air, is going to be divided by the sine of the angle of refraction, which is in this medium, the water medium. So that is going to be symbolized by R. So in this case, I is actually 40 degrees. R is actually 29 degrees. So let's go ahead and solve for the refractive index in this case. So the refractive index is going to be N is equal to sine angle of incidence is actually 40 degrees, and this is going to be 29 degrees for this angle. And when you solve that one, you're going to discover that the refractive index is going to be sine 40 over sine 29 is going to be 1.33. So this is the refractive index of water. So the refractive index of water is actually 1.33. Now, what about the critical angle? Well, when you're talking about the critical angle, you might have something like this. Let's say this is the dense medium, which is water, and this is air. Let's say this is the normal. So when light comes in this direction, sometimes, let's use the white. When light comes in this direction, it becomes parallel to the resting position here. In other words, the angle of refraction here becomes 90. So when we are talking about the critical angle, we are talking about this angle of incidence, whose angle of refraction is actually at 90. So this particular angle here is what we call a critical angle. Now, the conditions for this to take place, light has to be traveling from a more dense medium like water into a less dense medium. Not only that, the angle of refraction must be at 90 like this. Now, if this, let's just assume that this angle of incidence is actually extended to this position. It means that what is going to happen is something called total internal reflection is going to take place, because this is going to reflect like that. So it doesn't pass through to the next medium. Instead, it reflects internally. So that is what we call total internal reflection. Now, the formula for the critical angle is actually given by 1 over the refractive index. So in this case, we can go ahead and find the critical angle. So this sine C is going to be, we know that the refractive index in this case is 1.33. So this is going to be, we are going to have 1.33 sine C is equal to 1. So we can now reduce this by saying over 1.33 sine, because we want to remain with C, over 1.33 sine. So this is going to give us the critical angle is equal to, now we can change this. This is going to change into sine inverse, and then for 1.33 is also going to be 1 over 1.33. And when you do that, then you can solve for C. So the critical angle is going to be, when you do the math here, you're going to get 48.8 degrees, which is essentially just 49 degrees. So this is our critical angle. So the critical angle here must be 49 degrees. So make sure you understand how to find the refractive index using Snell's law, and also finding the critical angle, understanding what the critical angle is, and also understanding what total internal reflection is. These are important concepts that can help you understand these principles. Question B7 says, figure B7.1 is a diagram showing a 240 volts main supply connected to a television set and two lamps. So this is the diagram. You have a television set with two lamps. So this is the television set and these are the two lamps. Now the statement says the power supply to each lamp and television is 40 watts and 120 watts respectively. So since you have two lamps, notice that you have 40 watts at each lamp. That is when the switches are closed. Now, the first question is calculate the total power supplied. Now, since this is connected in parallel, notice that this is a parallel connection. The total power supplied when you're dealing with parallel connections is actually the sum of the power of each component. So you have three components here. The total power supply is simply the power supply at the two lamps and also at the television. So you're going to have 40 watts plus 40 watts plus 120 watts, which is going to give you 200 watts. So that is our answer. Now what about the second question? The total number of kilowatt hours of energy supplied to the circuit in 3 hours. What would you say? Now, notice that we are dealing with the total energy in kilowatt hours for 3 hours. Now, energy is given by power times time. We have power, we have time here. The time is actually 3 hours. This is the formula that we are going to use. Now, since this should be in kilowatt hours, then this power which we have has to be converted into kilowatts. So you can convert 200 by dividing it by 1000. So you're going to get 0.2 kilowatts. So that's the new figure that we are going to get for power. Then we can go ahead and solve for energy. So we are going to say energy is actually going to be 0.200 times 3 hours. And this is going to give us 0.6 kilowatt hours. So that's the amount of energy that are going to be supplied to the circuit in 3 hours. So make sure you understand how this is done, especially when you're dealing with energy. This is the standard formula that we use. Energy is equal to power times time. So make sure that you have power, you have time as well. If power is in watts, please convert it, especially when you look at the question, how it has been asked and what is needed. Now, question 3 says, calculate the potential difference or the voltage across the television set. What would you say? Well, when you go back to this question, you notice that here you have a television set. So this is the television set and you have the two lamps. Notice that the potential difference of the voltage that is being supplied is 240. Now, since this is the parallel connection, you have to understand that the potential difference across each circuit is actually the same. So the potential difference supplied to the television and the potential difference or the voltage supplied to the two lamps is actually the same. So when you're talking about the potential difference that reaches the television, it is still the same potential difference here, which is 240. So 240 volts is actually the answer for this particular question. So make sure you understand how to deal with these problems. So while the power here is 200 watts. The energy is actually 0.6 kilowatt hour, and the potential difference is actually 240 volts. Question B8 says, figure B8.1 is a diagram showing a coil of wire wound on a soft iron core with current flowing in the direction indicated by the arrows. So this is the figure. The first question says, mark the north and south poles induced on the iron core. Well, again, remember how electromagnets are made. And you should also remember how to use the right hand grip rule. So in this case, since you have the direction of current, it means that it is going to flow in this direction. So to determine the poles that you have at the end of this electromagnet, you have to use again the right hand grip rule. So this is the thumb, and you're going to have so for this one it's going to be like this, and then like this, and then like this, and then like this. Notice that this is the right hand, not the left. So these fingers are trying to show the direction of current. Notice the direction of current here. It is moving from the left to the right. So this is similar to what we have here in the right hand grip rule, because you have to position the fingers according to the direction of current. So make sure you do that. And this thumb is going to show the direction of the magnetic fields. The direction to which it points is actually going to be the North Pole. So obviously here you're going to have the North Pole because that's where the thumb is pointing. And here you're going to have the South Pole because that's the other alternative that you're going to have. So this is how we answer the first question. Use the right hand grip rule, pay attention to the direction of current, and you're going to have the poles at each specific point. Now the second question is, show by an arrow the direction in which the plotting compass needle would point when placed at point X. Well, again, you just have to use the same right hand grip rule, and you want to understand that when the compass is actually placed at point X, it is going to point in the direction of the magnetic field. So just like when you use the right hand grip rule, the direction of the magnetic field is actually in this direction. So this compass is also going to point in this direction. So that's how you show it. It is going to point in that particular direction because that's what the right hand grip rule is going to tell you. Whenever you see that this is the direction of the magnetic field, just know that the compass is going to point in that direction. Now, for question C, it says a beam of electrons flows through point Y in the direction perpendicular downwards into the paper. Show clearly using an arrow labeled F the direction of the force exerted by the magnetic field on the electron beam. So how do you demonstrate that one? Now, when you're trying to determine the direction of force exerted by the magnetic field, when you're talking about the electron beam, at this time what you use is what we call Fleming's left hand rule. So Fleming's left hand rule. So how does that work? Remember that this is used when you are trying to show the direction of force, not really the direction of the magnetic field. If you're trying to deal with the direction of the magnetic field, use the right hand grip rule. If you are trying to deal with the direction of force, use Fleming's left hand rule. So this is how it works. So we are going to draw the hand here, and we're going to so these are the first two hands, two fingers, and you're going to have the finger here and the finger there, and you are going to have also the thumb. So this is the left hand. So what is happening here is that the direction of the thumb is showing the direction of force, and the direction of the first finger is showing the direction of the magnetic field. And this finger here is showing the direction of current. Now, usually what happens is that when electrons are moving in a certain direction, the current in the wire is going to go into a different direction, in the opposite direction. That is conventional current. It is going to go into an opposite direction. So just keep that in mind. When electrons are moving in, current moves in the opposite direction. So that is the principle that you have to understand. Now, in this case, the question is, a beam of electrons flows through point Y in the direction perpendicular downwards into the paper. Now, since electrons are moving in this direction, they are moving in the direction of the magnetic field, because remember, according to right hand grip rule, that is the direction of the magnetic field. Now, if you try to change this, because since this finger is pointing to the direction of the magnetic field, then it should point to this direction, because this is the direction of the magnetic field. And since electrons are moving into the page, then the current has to move out of the page. That's the principle, because remember, when electrons are entering, current is going to go into the opposite direction. So this current has to go out of the page. So it's going to go out of the page like that. So when you use this rule, you're going to see that the first finger is going to point in this direction. And here you're going to have the two fingers, and this finger is going to show the direction of the conventional current, and the thumb is going to point downwards, because current has to go out of the page. That's how we show current moving out of the page. It is in the direction from where you are standing. It is more like it is coming out of the screen. So that is the direction of current. And then that means that the thumb going downwards is going to show the direction of the force exerted by the magnetic field on the electron beam. So that's basically what is going to happen. Here you have the direction of the magnetic field, here you have the direction of current, and here you have the direction of force. So with that in mind, you can clearly see that the force is going to go in this direction. So this is going to be force. So that's how you show the direction of force, the direction of magnetic fields. Make sure you understand the principles of Fleming's left hand rule and right hand grip rule. Now, question B9 says phosphorus 32 can decay by emitting beta particles. Now, the first question is, what is a beta particle? Now, the first thing that you want to understand is that there is what we call the radioactive isotopes. These can decay and they produce radiations. When they decay, they produce radiations. Now, these radiations can be alpha radiations, beta radiations, or gamma radiations. So these are the emissions from these radioactive isotopes. Now, when these are emitted, especially the alpha and the beta, they try to change the number of protons or the number of neutrons of each particular atom. So, for example, in the case of the beta emission, usually when you're talking about beta emissions, a beta particle is a fast moving electron emitted from the nucleus. So this is a fast moving electron emitted from the nucleus. What happens is that a substance may emit a beta particle, but when it emits a beta particle, what is really happening is that a neutron in that particular atom is actually changed into a proton and then an electron which is emitted as a beta particle. So this electron is emitted as a beta particle, but a neutron is actually changed into a proton. And so because of that, the atomic number of this particular atom increases. It increases by 1. Why? Because the atomic number is actually the number of protons in the nucleus of an atom. So if one neutron is changed into a proton, then the number of protons actually goes up. Therefore, the atomic number goes up by 1. So make sure you understand that. For an alpha particle, the alpha particle actually has 2 protons and 2 neutrons. So when an atom emits an alpha particle, it means that it loses 2 protons and 2 neutrons. So then when, let's say uranium, when uranium-238 releases 1 alpha, then since the alpha particle has got 2 protons, then the atomic number is going to reduce by 2, so it's going to be 90. Whereas the mass number is going to decrease by 4, because the mass number is the number of neutrons and protons in the nucleus of an atom. Since you have 2 protons that are lost and 2 neutrons that are lost, then this is going to decrease by 4. So you're going to have 234. Actually, this H is going to change to TH. This is thorium. So you're going to have thorium because everything has now changed here. And then you're going to indicate that the alpha particle has been lost. And this is actually the same as helium. So usually we just say helium because it is the same structure as the alpha particle. So this is how you're going to write the equation when an atom releases an alpha particle. If it is 2 alpha particles, you just have to calculate accordingly because 1 alpha particle has 2 protons and 2 neutrons. So make sure you understand that. Question B is saying if the proton number of phosphorus 32 is 15, state the new values of proton and mass number of the nuclide just after it emits a beta particle. So when it emits a beta particle, remember that when a beta particle is being emitted, a neutron changes to a proton, which means that the atomic number increases. So initially we have 15. So this 15 is going to change to 16 because the proton number increases by 1 when one neutron changes to a proton. So the proton number is going to be 16. The mass number is not going to change. Why? Because notice that it is a neutron that is being changed. But it is not being lost, it is being changed into a proton. So like, let's say sodium, just an example. Sodium has 23 as the mass number, which means that you have 11 protons and 12 neutrons. So this is the total of the mass number. But if you lose one neutron and actually add it to the protons, then you're going to have 12 protons and then you're going to have 11 neutrons. So the number still remains. So the mass number doesn't change. So the mass number is just going to remain the same since this is phosphorus. So it is phosphorus 32, which means that it is still going to be 32. Now, the next question is write the decay equation for phosphorus 32 after emitting 2 beta particles, which means 2 neutrons are going to be converted into protons. So the first thing that you want to write here is you write the phosphorus atom, which is P, and then here you have the atomic number, which is 15. Then after it emits 2 beta particles, the atomic number is going to increase. The mass number is not going to change. So this 15 is going to increase by 2 because 2 beta particles have been released. And when you have something like that, you will notice that it is going to change into chlorine atom, because here you're going to have 32, here you're going to have 17. So this is chlorine, and you're going to indicate that it has lost 2 beta particles. So we write it like this. So on top, and then at the bottom, because 1 beta particle has been lost, so you indicate by -1, and that beta particle has to do with the electron because it is the number of electrons. This is an electron which is lost. So this is how you write the equation for the decay of phosphorus. Now the last question here is phosphorus 32 can be used to prove that plants absorb phosphorus nutrient from the soil around them. State one safety precaution which should be taken into consideration when doing experiments with phosphorus 32. Now, because phosphorus 32 is a radioactive substance and it emits these beta particles which can be damaging to the living tissue, then you have to use gloves, protective gloves, when handling the source. So you have to use protective gloves. So make sure you understand that the reason why you are using protective gloves is because this is a radiation. It emits radiations like beta particles which can damage the living tissue. So this is what we can say about beta radiations. About alpha radiations, remember that the alpha particle contains 2 protons and 2 neutrons. So when 1 alpha particle has been emitted, then just know that the atomic number is going to decrease by 2, whereas the mass number is going to decrease by 4. But when the gamma radiations are released, the atomic number and the mass number do not change. Only energy is actually released. So that's another important point that you want to be familiar with. Now for section C, we have the first question, which is saying figure C 1.1 below is a velocity time graph representing motion of a motor cycle traveling along a straight road. So this is what we have. This is the velocity time graph showing the movement of this motorcycle. Now, the first question is describe the motion of the motorcycle between the points O and P, P and Q and R. So when you look at O and P, this is between this point and that point. How can you describe the motion of a car during that particular moment? Well, when you look at O and P, you will notice that this is what we call the uniform acceleration, because the velocity here is increasing at a constant rate and the gradient is actually positive. So this is showing uniform acceleration. Then for P and Q, what do you think is happening around that time? Well, the fact that this is representing the velocity, and at 40 the velocity remains constant, then this is showing constant velocity. And for Q and R, notice that this is the initial velocity, this is the final velocity. It's the same as this particular slope, except that this is going down, this is going up. So in other words, this is positive acceleration, this is negative acceleration. And the negative acceleration is actually what we call deceleration. So we can say this is uniform deceleration. So make sure you understand these key points because they'll help you figure out what is happening at which particular point. Question B says, what is the maximum speed of the motorcycle? What would you say? Well, when you look at the graph, you'll notice that the maximum speed is actually at point P, which is 40. This is the maximum speed reached by this motorcycle. So you can go ahead and say that the maximum speed is actually equal to 40 meters per second. Now for question C, we have the question which says, how long did it take the motorcycle to retard to rest, to decelerate to rest? Well, notice that the car began to decelerate at this point. And when you look at the graph here, this was at approximately second 7. So this is around second 7. And from 7, it comes to rest during second 12. So from 7 to 12, that's how long it has taken for this motorcycle to actually come to rest. So that is going to be 5 seconds. So as you can see, this is not even difficult to understand. You can just look at the graph, understand what is happening, and then you have the correct answers. Now question D says, calculate the total distance traveled by the motorcycle. Now, for you to calculate the total distance, you have to understand that distance is equal to the area under the graph. So in this case, if you find the area of this particular figure, then you get the total distance traveled by this motorcycle. So that's a very important point to understand. Whenever you're dealing with distance on the trivial graphs, just know that it is equal to the area under that particular graph. So you can either use the area of the trapezium, or you just cut off the triangles that you have, because here you have one triangle and here you have another triangle. So you have triangle A, and you have this rectangle B and another triangle C. So you can calculate them independently and get the final answer. So let's go ahead and do that. So let's say the area of triangle A is actually going to be half BH, because that's the formula. So this is going to be, what's the breadth here? And 2 into 40 is 20. 20 by 3 is 60. So this is 60 meters. Then the area of C is going to be half. And when you look at the part here coming down, you see that between this and this, we calculated it to be 5. So this is going to be 5 times the height is actually 40 as well. So this is going to be 40. So this is going to be 2 into 40 is 20. 20 by 5. So this is going to be 100 meters. And now we can find the area of B. So the area of B is simply L times B. So between 3 and 7, you're going to have 5. So this is 5 times 40, which is the height. So this is going to give us 180. So 180 plus 100 is 280 plus 60 is going to be 340 meters. So this is the total distance traveled by this motorcycle. So just make sure you understand that when you calculate the area of the figure given, then you have found the distance of that particular figure. Now, the last question here is calculate the average velocity for the entire motion, for the whole motion. The average velocity is actually the total distance traveled over the total time. So in this case, the total distance is 340 meters, and the total time, notice that this is 12, so it is 12 seconds. So the average velocity is going to be 320 divided by 12 is going to be 26.67 meters per second. So that is the average speed. Now, question C2 says, Elena carried out a Hooke's law experiment and obtained the following results. So this is the table showing the Hooke's law experiment results. Now, the first question is copy and complete table C2.1 by finding the values of applied force N and extension in millimeters produced. So how do you deal with that one? Well, when you're talking about what is happening here with the extension, you might have something like this, and then you hang object A to it. Let's say this is having 10 newtons, and the distance here is, let's say, 10 millimeters. So if you increase the weight here, or the force, to, let's say, 20 newtons, you see that this is going to extend from this to somewhere here. So we want to find the force applied and also the extension that is going to be produced according to Hooke's law. And this Hooke's law is actually a law that explains that as long as you are within the elastic limit, in other words, in the region where there is elasticity, this can be stretched, then the extension that you're going to have of a spring is directly proportional to the applied force. So when you apply the force of 20 newtons, it is going to increase proportionally like that until you reach the limit of proportionality. That is the limit beyond which you cannot stretch this further, or rather, this is the point where this proportionality is disturbed. So let's go ahead and fill this box. Now, for your own information, force is equal to mass times, in this case, it is gravity. So we just have to find the force for each area. In this particular case, we have the masses which are given here. So we have to use those masses for each particular phase. So for this one, the applied force for column 1 is actually mass is 0 times gravity, which is 10. So we are going to have 0 as the applied force. Not only that, the extension is actually the original length subtracted from the new length. So this original length has to be subtracted from the new length. That's when you get the extension. So with that, we can actually see that when you look at the extension here, it is actually essentially 0 because no force has been applied here. Notice that the force there is actually 0. So even the extension is going to be 0. So we're going to put 0 there. Now for the second column, force is equal to mass, which is 0.02 So mass is 0.02 times 10. So that is going to give us 0.2. So we're going to have 0.2 here as our force, which means that for the extension, it should be this 12.1 minus 11 is going to give us 1.1. But this 1.1, notice that it is in centimeters. So we have to convert it into millimeters because the extension is actually in millimeters. So you multiply this by 10 and you're going to get 11. Now you can do the same for the second one. This is 0.04 times gravity, which is 10. So we are going to get 0.4. And this 13.2 minus 11 for the extension is going to give us 2.2. Now 2.2 into millimeters should be multiplied by 10, which is going to give us 22. And the same is true at this particular point. The force is going to be 0.06 times 10. It's going to give us 0.6. And the extension is 14.3 minus 11, the original, which is going to be 3.3 times 10 into millimeters. It's going to give us 33. The same is true here. We're going to get 0.8 for the force. And for the extension is 15.4 minus 11. It's going to give us 4.4 times 10. It's going to give us 44. And here 0.1 times 10 is actually going to give us 1. Now the extension is 16.5 minus 11 here, which is going to give us 5.5 times 10. That is going to give us 55. So that is how we are going to fill that particular box. So make sure you understand how that is done. Now the second question is plot the graph of applied force N against extension. So use these values to plot the graph. So you can plot the graph like this. So here you're going to have applied force in newtons, and here you're going to have the extension in millimeters. So for the extension, you have 0 to 55. So we are going to say 0, let's say here 11, this is 22, 33, 44, 55. And for the force, you have 0.01, and you're going to have 0.2, you're going to have 0.4 here, and 0.6, and 0.8, and 1. So this is what we are going to have. Then we can plot the points here. So the first one is 0, 0, which is here. So this is the starting point. The second one is 0.2, 11, 0.2. So 11, 0.2 is going to be at this point, and 22, 0.4 is going to be at this point, and 33, 0.6 is going to be at this point, and 44, 0.8 is going to be at this point, and then 55, 1 is going to be at this point. So when you connect the line, notice that you have this straight line, and that shows that this line is obeying the Hooke's law, because the extension of the wire is proportional to the force applied, and this is what is happening. So this obeys Hooke's law in that particular case. Now question C says, from the graph determine the spring constant. Now the spring constant is actually equivalent to the gradient or the slope. So all you have to do is you can calculate the gradient here which is going to be y2 minus y1, x2 minus x1. Now we can get the y-axis, we can get 1 here minus the starting point here, which is 0, over x2 we can get 55, which is the maximum point, minus 0. And when we calculate this, we are going to get 1 over 55, which is 0.01818 Newton millimeter. Now, since this should be in meters, we need to convert this. And when we convert this figure into meters, K, which is the spring constant, is actually going to be what we have here multiplied by 1,000. So this is going to be 0.01818 times 1,000, and this is going to give us, essentially this is going to be 18.2 Newton per meter. So that is the spring constant that we are going to have. Now the question for D1 is that, did the spring reach its elastic limit? And the answer is no, because if there was the elastic limit, the graph would have gone this way, showing that the proportionality has ended. But we haven't seen anything like that, which shows that there was no limit of proportionality or elastic limit observed. The second question is, explain your answer in D above. Well, I've just explained that. It shows that there's a constant ratio between these two figures that we have. It is not bending, it is just a straight line through from the origin, which confirms that the elastic limit is not actually extended. So make sure you understand how Hooke's law works, elastic limits, the limit of proportionality. These things are very important when it comes to discussing forces. Now, our last question here is C3. Figure C3.1 is a chart showing some components of the electromagnetic spectrum. So this is the figure C3.1. Now, question A1 says, use the list below to copy and complete the electromagnetic spectrum chart. Radio waves, X-rays, ultraviolet, gamma rays, infrared, and red light. What you need to understand is the first one should be the gamma rays. And this should be followed by the X-rays, which are then followed by ultraviolet, which is then followed by the blue light here, which is followed by green, which is then followed by red light, and this is followed by infrared, which is then followed by microwaves. And lastly, you have the radio waves. So this is the arrangement of these electromagnetic components. Make sure you understand this. And these are actually arranged in the order of increasing wavelength. So the wavelength is increasing, but the frequency is actually decreasing. So this means that when it comes to the gamma rays, they are the lowest in terms of the wavelength, which means that the radio waves are the largest when it comes to the wavelength. The opposite is true for frequency. So make sure you understand this. Now, Question 2 says state 2 properties common to all members of the electromagnetic spectrum. Well, first of all, these are all transverse waves. Not only that, all these waves travel at the speed of light in a vacuum. So they travel at the speed of light in a vacuum, which is essentially 3 times 10 to the power 8 meters per second. Now the other property is that they don't need a medium because they can travel in a vacuum. And they also transfer energy without transferring matter. But you can just choose 2 from these because the question says state 2 properties common to all members of the electromagnetic spectrum. So these are some of the properties of these waves. Now, for B, the question says, name one component of the spectrum that has the longest wavelength. Now, notice that as you move from gamma rays, the wavelength increases, which means that the last one here, which is radio waves, is the one with the longest wavelength. So here you can say radio waves. But radio waves are the ones with the lowest frequency because frequency actually increases as you go to the left. So when it comes to the wavelength, it is radio waves, and gamma rays are the least with the lowest wavelength. But when you're talking about the frequency, you go in the opposite direction and you see that radio waves actually have the lowest frequency. The next one is name the component of the spectrum that is emitted by hot objects or hot bodies. Well, obviously, you know that this has to be the infrared. Usually, even at normal temperatures, hot bodies like human beings, usually even stoves, they emit infrared radiations. So you go for this particular component. Now for C, it says microwaves have a frequency of 10 to the power 10 hertz and the velocity of 3 times 10 to the power 8 meters per second. The first question is calculate the wavelength of microwaves. Well, this is straightforward. Speed of a wave is equal to the frequency of the wave times the wavelength. In this case, the speed is 3 times 10 to the power 8, which is equal to the frequency is 10 to the power 10, and we have the wavelength. So the wavelength is going to be 3 times 10 to the power 8 over 10 to the power 10, which is actually 3 centimeters, but in meters you can write it as 0.03 meters. So that is the wavelength of microwaves. And the last one says that state 2 practical uses of microwaves. Well, you use microwaves in cooking. You also use microwaves in satellite communication. And even in mobile phone transmission. So mobile phone transmission. And also things like Bluetooth, Wi-Fi, they use microwaves. So you can say in wireless networks. So make sure you understand how electromagnetic waves actually work. Study the electromagnetic spectrum, know how to arrange these components of the electromagnetic spectrum, know their properties and their uses, and then you are good to go. So that's it for this video. Thanks for watching.